Okay, but in table A20 previously, most of the material is from ductile. So because they're using we call carbon steel. Carbon steel. So for carbon steel, so the graph should be like this lah. Okay. Okay, and then equilibrium. Equilibrium, assume that the system to be studied is motionless or at most have constant velocity, then the system has zero acceleration. So under this condition, the system is said to be in equilibrium. For the equilibrium, the forces and moment acting on the system balance such. So when we're going to calculate the force acting at the any part, okay, you need to use this equation in order to calculate the other forces. Okay, so first you can use total acting force will be zero, total acting moment will be zero. Another one is total acting torque also will be zero. So this condition is we set it in equilibrium. Okay. Then from that one, we're going to draw the free body diagram. So what is the free body diagram? The free body diagram used to simplify the analysis of a very complex structure or machine by isolating or freeing a portion of the total system in order to study the behavior of one of its segments. So this free body diagram is essentially a mean of breaking a complicated problem into manageable segment, analyzing this simple problem, and then usually putting information together again. That's when we try to simplify the system before we can calculate. So let's say, so this is about the gear reducer. Okay, so they're given you the information, the torque will be given. Actually, this one is I made some mistake here. The unit will be pounds inch for the torque, pounds inch. Okay, so the torque is given 240 pounds inch. So the torque is actually at the input shaft. Okay, so mostly for the input shaft, we can get the information because we using the standard motor. Let's say 5 kilowatt motor or 1 kilowatt motor. From that information, 1 kilowatt motor, you can see from the catalog. So what is the torque and what is the maximum torque or the rated torque, and then what is the maximum or the rated speed at the motor lah. So we can get both torque and speed at the input here. And then if you want to calculate whether the shaft will be safe or not, you need to transfer all the forces acting at the shaft, and then you need to calculate the stress, the stress at the shaft. So the critical condition will be at the maximum stress. Okay, so from where is the location of the maximum stress? If the maximum stress is acting at this point, then the shaft will be fractured and become failed at this point. If the maximum force is maximum stress will be acting at this point, and then this one will be failed at this here. It will crack at here. So that's why we need to calculate maximum stress. And then from that stress, you want to compare it with the strength that we have, the strength that we have here. So what happened if the stress beyond the yield? So you can see the shaft will become deformed, and we have a permanent deformations. So what happened if the stress is bigger than ultimate? So it will become fail, become fail after a few minutes. Okay, so that's why we need to calculate the maximum stress, and then we want to compare with the strength of the material. Okay. So from here, from the exercise here, okay, so the first thing, let's say you want to calculate the stress. Before you can calculate the stress, you need to draw the free body diagram of this thing. Okay, so let's do the free body diagram. So let's say this is the shaft. And then where is the pen? Okay, so we have a torque at here, the torque here. Okay, when I transfer it at the free body diagram, so we just follow the direction. Okay, so this is the top. And then so because we have a equilibrium theory, so we have a torque that acting at the clockwise direction. So we need to put a torque that acting counterclock direction. So which is the torque will be at the gear. So we need to put here the gear. This is the torque. Maybe torque in. So the torque will be going out at the gear. Okay, and then after that, if you can see here at the gear here. So let's see. This is your gear. So in order to produce the torque that acting in this direction, okay, you need, and then you can see that the gear is touch the gear number 2, gear 1 touch gear number 2. So there will be a force at the gear. Okay, so there will be 2 force at the gear, which is the F from the tangent of the gear, and this is gear number 1, and then we have force which is acting at the radial at the gear number 1. Okay, and then this is the top. And then when you transfer these 2 force at the gear, so you need to just follow the direction. This is your FR, and this is your FT. Maybe I can put the X, Y, and Z direction. And maybe at the top here is your Y direction. Here will be your X direction. And here is your Z direction. Okay, so X, Y, and Z direction. Okay, and then after that, because this shaft will be support at bearing B and A, so we will have a reaction force. This one is action force, FT and FR, because this one is direct from the top here. And then we have a reaction force at B and A. So the reaction force will be opposite direction of these two. Okay, so I need to put this one, the force getting at here, which is BZ. And also this one is top. Okay, we have downward force here. This is BY. Okay, and then we have A here. So we have AY. Okay, and then we have also AZ. Okay, so you can see all force will be complete already. Okay, we have action force and we have reaction force, and this we have two top to make sure it's in equilibrium. Okay, so after that, you can before you can calculate the stress inside here, you need to know all the force value. Okay, so we have already drawn the free body diagram. We have already put the name for each forces, and then you need to calculate the value of the force. So how you want to calculate the value? So you need to start from information that you have lah. Let's say this one you have 240 pounds inch, okay, which is your top at the top in here. So top in will be equal to top out because we are going to use the equilibrium for top. Total top will be equal to 0. So this is the equilibrium theory. Okay, so top in will be equal to top out. So which is top out is equal to the same value lah, 240 pounds inch. Okay, and then because the radius for the gear is given 0.75 inch, okay, that's mean we have a radius for this one. Okay, actually you can calculate the top, this one is the top out. So the top out is equal to this one Ft times the radius. Okay, and then you can calculate the Ft value is equal to top out divided by the radius. And then top out is 240. The radius will be 0.75 inch. Divide 0.75. Okay, so you get the 320 pounds. Okay, so this is your Ft. And after that, the Ft and Fr, so we have some relation here. There is a gear pressure is about 20 degree. So if you notice that the gear load will be acting about 20 degree. So let's say this is your pinion. This is your gear number 2. Okay. So from this one you have line from here, the normal line, and then we have line at here. So the gear force is acting at this one F. Okay. So you have already know your F here, Ft. You want to calculate your Fr. And Fr actually at here, but I transfer to here, Fr. So if you look at this one, if you look at the trigonometry of this triangle, you have here, here, and here. Okay, so this is your E, and this one is your Fr, and this angle will be 20 degree. Okay, so you can calculate your Fr by using the trigonometry theory lah, which is tangent 20 degree is equal to Fr divided by Ft. Okay, and then Fr is equal to, you can calculate Fr, is equal to Ft, which is 320 times tangent 20 degree. Okay, Ft is 320. Okay. 20 degree tangent. 0.36 0.364. Maybe can someone check whether the calculation is correct or not, because I don't have the proper calculator inside here. 116.5. Is it correct?
Yes, Doctor.
Okay. Okay. So we have FT, we also FR. So from here, after you have this value, we have two unknown here. We have one value that you already calculate. You can use the equilibrium theory to get the rest lah. Let's say, so you need to separate. So you need to separate this 3D diagram into 2D axis because it's much easier lah to calculate. So let's say if I look on y-x axis, y-x-axis. Okay, so y-x-axis, the shape will be going to be look like here, y-x, and the force that acting on y and x-axis is by. Okay, and then we have on y-axis here we have Fr. Okay, and then we have Ay. There is no more. Okay, Fr, the value is 116.5. And what is the distance? The distance actually is on next page, which is 1.5 and 1 inch between these two bearing. So tadi 1.5, 1 inch. Okay, so in order to calculate by and ay, because we have two unknown here, you need to cancel one. So that's one. You need to use the theory for the moment first. So total moment, okay, acting on this one is point B, okay, moment acting on point B that follow on Z direction will become 0. Okay, this one is actually because we call it MBZ. So why we call MBZ? B actually at the point B. Okay? If you calculate moment at point A, you put A. And Z is actually the direction, direction of the moment here. Okay, if you look here, so we have a moment, we want to calculate moment in this direction. So actually, the direction that you're going to put the name here is on Z because it rotates on Z axis. And this one is Z, Y, X, and this one the normal to the your monitor is Z. So that's why we call it MBZ. Although you calculate this one Y and X axis. Okay, so this is the standard. You need to recheck again at the textbook. Okay. So the total moment acting on point B at rotate on Z direction will equal to 0. So we have this one will be cancelled because I think there is no no distance here. So we start with Fr. Fr time 1.5 because I assume counterclockwise will be positive. Then minus Ay, the distance will be 2.5 is equal to 0. Okay, and then so you can calculate your Ay. Ay is equal to Fr is 116.5. Then times 1.5 divided by 2.5. Okay, can 1.6.5. 116. Okay. So you will get 69.9. Oh. Okay, and then after that, this one is AY 69.9. Okay, and then after that you can calculate your BY lah. So BY you can use the total force acting on Y is equal to 0. So maybe I put upward will assume positive. So 116.5 minus AY. AY is 69.9. And then this one you will get your BY lah, BY. Okay, so you get 47, 116.9, or 116.5. 46.6. Okay, so you can get your BY. So you already complete lah for the Y X axis. Okay, and then after that, you need to calculate on Z and X direction. Z and X direction. Okay, for Z and X direction, we draw again. Okay, so then for here you can see Z is acting downward and downward if you look at the top plane, and X will be on your right. Okay, and then you put the force. You can see you have BZ, and then we have FT here, and then you have AZ. Okay, and then the value that you have is FT. FT. Where is it? FT. 320 pounds. 320 pounds. Okay, and then the same technique. If you want to calculate BZ and AZ, you need to calculate at the moment first. So total moment acting at the point B here. Okay, that rotate on this direction. Okay, so this direction will be on which axis actually? Mana? X, Z, Y. So M dy is equal to 0. Okay, so 320, and this one the same distance, which is 1.5. Okay, and then AY minus, because it's acting clockwise direction. AZ, the distance will be from B here is 2.5. Is equal to 0. Okay, and then you can get your AZ. AZ is equal to 320 times 1.5 divided by 2.5. Okay, 192. Okay, and then after that, you can calculate your BZ. BZ is 320 minus 192. Then you will get 128 pound. Okay, so you already complete all the force acting on input shaft. Input shaft. Then if you want to calculate the output shaft, you make the same technique again, same method again, but this time you start with FT and FR at the gear number 2. And FT, FR at the gear number 2 will be the same value, because this one, you can see here. Okay, so if you draw the free body diagram of both gear, okay, so this is the pinion, so you have FT, FR. Then for the gear, the same, you have the value, the same FT and the same value of FR here. Okay, so just use the same value, but this one we have different radius. Okay, maybe the top will be different lah. Okay, this one R2, this one R1. Okay, only the difference is top, but if you look at the calculation of force here, there is no top calculate in this year. Just the top here we are going to use to calculate the FT and FR at the gear. And then after that you can calculate everything lah. Okay, so any question? Ada yang tanya apa-apa? Ada. Okay, so if you try to compare the answer, so there is an answer of here. Okay, so RAY here 192. I think the same. Mine is AZ. AZ 192. Okay. And then maybe BY is here. What is it? BY is 46.6. Okay. BY here. Here RBZ 46.6. Okay. Only the name is different. The answer is same. So the rest I need you to do by your own. Try, because this one is you already learned. Okay. So this is the answer for the force. And then from this force, actually, we are going to calculate the stress, because we want to make sure whether the part is safe or not. You need to calculate the stress, and then from the stress, you need to calculate where is the maximum stress, where is the critical location. So we believe that at the critical location or the maximum stress, the crack will start at that point. Okay, so then we want to check whether this part will safe or not. We want to compare the value of maximum stress with the strength with the strength of the material. Okay, if the what you call, if the stress is bigger than the strength, so the part will be fail. Okay, so this is the general theory. We don't want the stress become bigger than the strength. Okay, so if the stress is less than the strength, the part will be safe. Okay, so we are going to calculate everything by using this general theory lah. Okay, so from that force, okay, so you can see that there are few of force: tension load, compression load, bending load, torsion load, and shear load. So from all these force, if you want to calculate the stress, you need to use a different equation. Not everything to calculate force is F is equal, stress is equal to force divided by area. It depends. For tension and compression, maybe you can use force divided by area. For bending, torsion, and shear load, you need to use other equation to calculate the stress. Okay. So we're going to look. So what is the formula? So okay. So before we use the formula, so you need to know there are two kind of stress. The first one is we call it as normal stress. So normal stress is actually acting normal to the force. Okay, so let's say this is the force, and if you want to calculate the stress, you can calculate the normal stress, and the stress will be acting normal to the force here. And then the other one is a shear stress. Shear stress is always happen inside, inside the part. So always inside the part. So for normal stress, we just put it. The symbol will be sigma, and for the shear stress, the symbol will be tau here. Okay, so this is there are two kind of stress, sigma and tau. Okay, so from this, all these forces, okay, some of the force will produce a normal force, and some of it will produce a shear force. Sorry, not shear stress, shear stress. Okay, so for tension load, you can see, okay, it will produce normal stress, sigma. For compression load also will produce sigma. For shear load, it will produce a shear stress, which is tau. And for torsional load, it will produce also shear stress, which is tau. And for the bending load, it will produce both. It depends on the location. If you study at the top, it will produce normal, or we call normal stress, which is sigma. And if you study at the shear, will produce the tau. Okay, for just for bending load. So we have both kind of stress, normal stress and also shear stress. Okay. Okay. So so mostly the critical location will be happen at the outer diameter. Let's say if you have a road, if you have a road, okay, and then you apply whether torsion. Okay, let's say you apply torsion. So we have torsion here. So if you look at the formula, the torsion will be produce shear stress. So shear stress is equal to TR over J, where R is equal to D over 2, and J will be pi D power 4 divided by 32. Okay. And then you can simplify this equation. You can see this one is D power 4. This one we have D. So this one we cancel D power 3. And 2 and 32 we can simplify to 16. And then 16 you're going to put at the above. So the final equation will be 16T divided by pi D cube. Okay. So this is the equation to calculate the shear if you're having a torsion. Okay. Let's say, sekejap eh. 60 divided by D by Q. Okay. So actually, so mostly, the cracks will start happen at the outer, not at the inside. So that's why when you study, the critical location is actually start at the outer. Okay. So in here, when we study at the outer, we have only one. We call it as a plane stress lah. This is plane stress. So for the plane stress, this is the 3D stress. We can simplify it by using this one. Okay. So let's say if you this one is x axis, this one is z axis. Okay, and then the top here will be y axis. So y axis you can ignore it. Okay, you just study on x and z direction. So let's say this one. So if you have a load in x axis, it will produce stress and x axis. If you have a load on y axis, so you will have stress on y axis. Simple like that lah. So this one we call it as a plane stress. Then from that plane stress, okay, to get the maximum stress, okay, you need to have to use the formula. We have two formula here for to get the maximum stress. Okay, so this is the formula how you want to calculate the maximum stress, sigma 1 and sigma 2. The maximum stress is happen when we try to combine both stress on here. We have sigma x, so this one is sigma x, we have sigma y here. When you try to rotate this one a little bit here, okay, so you will get the value will become maximum. Okay, so we have two kind of maximum stress. This one we call it as the maximum and minimum normal stresses, which is sigma 1 and sigma 2. Then one is in for shear. Your shear is maximum tau 1 and tau 2. Okay, because we have two kind of stress. Okay, this one is combined. This one is combined from normal stress. We have sigma y, sigma and tau. And then after you rotate a little bit, so there is some location of some angle that we get this normal stress will become maximum. Okay, so that's why from sigma x here and sigma y here, we calculate sigma 1 and sigma 2, but there is no shear stress happen in principal stress here. When the normal stress is maximum, there is no shear stress happen here. And then the other condition here, when we rotate a little bit more, so your shear will become maximum. This one will become maximum, but your normal stress, it will become average. This one will become average value. So you need to check both. You need to check both condition. You need to calculate sigma 1. You need to calculate sigma 2. Okay. You need to calculate also sigma 3. But sigma 3 is actually at the normal to your monitor here. Let's say this one is y, x. The sigma 3 will be on z direction. So sigma 3 always 0 lah. This one is always 0. Okay. And then you need to calculate also in second condition, the shear will become maximum, which is tau 1, tau 2, and also tau 3. Okay. So there are two ways to calculate this value. Okay, the first one by using the equation here. And this is the equation to calculate sigma 1, sigma 2, tau 1, and tau 2. The second way, you can using the Mohr circle. Okay, but this one I think you need to draw properly on graph paper lah. So if you don't use the graph paper, then you cannot get the correct answer lah. So for the Mohr circle, So we have sigma x and sigma y here. And then we have tau xy here. And tau from here, we have this point and this point. And to draw the Mohr circle, you need to have this sigma x, sigma y, and tau xy. Okay, from here, sigma x, tau xy negative. This one, sigma x or sigma y, tau xy positive. We get these 2 points. From these 2 points, when you draw a line, so this line will cross at the 0 axis. This one on x-axis. So this one will be your radius or your diameter, and your diameter for the Mohr circle. And then from here, you take what you call jangka lukis, and then you draw a circle like this. Okay, and then from that, if the circle intersection with this one, you get the sigma 2, and then if you discuss intersection with the maximum value, you get your sigma 1. Sigma 1 and sigma 2, you can get from you can calculate from, or you can read from the graph paper lah. Okay, so this one by using the Mohr circle, but I not advise you to use this kind of method because it's take longer time. You just use this equation to get to calculate sigma 1 and sigma 2, tau 1 and tau 2, which is sigma 1 is sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 square plus tau xy square, and the answer you need to square root here. And then for sigma 2, this answer minus this value. You get your sigma 2. So actually, you get the same answer if you're using the Mohr circle. In 3D, in the 3D analysis, okay, so let's say let's say for 3D analysis, so let's say you have 3 principal stress. Okay, so the previously we just discussed for plane stress, which is we have sigma 1 and sigma 2. Sigma 3 we assume 0. But this one, if you calculate at 3D, so you in sigma 1 and sigma 2, you will get your first tau max. This one is tau max for number 1. And then for sigma 2, sigma 3, you get another tau max. This one is maybe tau max number 2. And then from the bigger circle here, you will get your the third sigma stress, which is tau max number 3. Okay, so in order to get the maximum shear stress, you need to look from this value number 1, value number 2, value number 3, which one is the biggest value. Okay, so actually the tau max is the biggest value lah. So in this condition, it is the biggest circle. It has happened at the biggest circle. So you're going to use this value to calculate in order to calculate the safety factor. Not this value or not this value lah. Okay. So this is just the technique to get the tau maximum value. You will get your 3 value of tau max, and then just use the maximum value in order to calculate the safety factor after this. If there any question you want to ask, please ask. If you need to have more explanation. Ada?
For now tak ada, Doktor.
This one we just review kan. Okay, and then the formula. Okay, so how to get your stress from each kind of forces. The first one, tensile and compression. For tensile and compression, the formula to get stress is F divided by A. So A is the area, cross-section area. It depends. If you're using the road, a circular road, so pi d square divided by 4. We are using rectangle, then B times D, and the width times the height of the cross-section. So it depends on the area lah. And then the same thing for the shear. For the shear, to get the shear stress is F divided by A. A is the shear area. Okay, it depends lah. If you put a bolt through the hole inside here, So the bolt is will become shear. Okay, not this one. If you weld this one, then you weld this one. This one is there is no bolt, and then you need to find this area lah. This is the W. Maybe what is the length over there? Okay. And then for the bending, if you want to calculate the stress, is MC over I, where M is the bending load, okay, and C is the distance from the neutral axis. Okay, so if you see, you can look here. So this is the neutral axis. Is mostly it will happen at the center of the beam. Okay, so C will be half of the diameter, or maybe half of the height of this one. And I is the second moment of area. Is depend on the shape of the beam, whether it is rectangle or circular. For rectangle, the I will be d cube, if I'm not mistaken. You can check. You can check that one in appendix. Appendix. Which one? Let's say appendix. Where is it? Table content. What is second moment? SI, option SI, physical constant, properties of structure, steel angle, properties of structure angle, steel beam, maybe A7. Okay, this one. Table A18. The name is property of section. From the property of section, so it will given you the I and J value. So I for rectangle is BH. BH power of 3 divided by 12. Okay, so H is here. B is here. Okay, so this is the cross section area. This cross section area. Okay, and for circular, I, X, and IY is pi d power 4 divided by 64. And the J value, J is the summation of IX and IY. Okay, so that's why IX and IY for J, for circular question here, you get pi d power 4 divided by 64 plus pi d over power 4 divided by 64, you get pi d power 4 divided by 32. The summation of this one. If the section is rectangular, so you need to sum these two things. Okay. Then after that, table 18 to find the J and I value. Sekejap Okay. Mana tadi Okay. So let's continue chapter 2. So this is how you want to get the I and J, table A18. So just put some notes here where you to find this value. Appendix. Appendix A18. Okay, and then after that, okay, so the maximum value of normal stress is always happen at the outer. As I mentioned before, okay, you can see if the C is larger here, then you will get your maximum stress. That's why maximum stress is always happen at the outer. Okay, so if you study maybe at the center here, the normal stress will become 0. This one, normal stress is equal to 0 at the center. Okay, so let's discuss how we want to calculate the bendings or the moment, the moment here. So let's say they given you the force. So let's say this one we have a pulley and a gear, and then from this one it will produce a force about 400 pound, and this one is 150 pound. And then after that, from these two force, you need to calculate the reaction force O and C here by using the equilibrium theory. Total force acting, total moment acting at O here will become 0. Total force acting at Y direction is equal, will become 0. Then you will get this one, 300 and 250, as I previously discussed. So after that, if you want to get the moment acting at the shaft, you need to draw these two diagrams. The first one is shear force diagram. The second one is bending moment diagram. Shear force diagrams is according to the value of the shear of the load here. So let's say you have 300 pound acting upward. So you have 300 here. And then there is no force between O to A, and then the load will become constant. We have 300 here, it will become constant 300. Then from A here, we have 400. So 300 minus 400, the result will be negative 100. So you just put a straight line here, and then from here, you get negative 100. And then there is no other force here. Then this means it will become constant, negative 100. Up to point B here, we have 150. Then this one, you add another more, negative 100, add another more 150. So you will get negative 250. Then for the last one is 250 upward, and then this one you will get 0 again. So you can see that in equilibrium theory, so you can see that the starting will be 0, and at the end also will be at the 0 value. So this is the equilibrium. And then from this one, if you want to get the moment here, okay, so you need to calculate the area inside the shear force diagram. Okay, so let's say if you want to calculate at here, so the moment at here, how we want to calculate? Let's say the moment at the middle, at the middle of here. So let's say this is at the middle of this one, 6 inch. Okay, let's say this one is about 3 inch. Okay, so you can calculate. We have force 300 and minus 300 times 3. 300 times 3, you get this one, and then one is 900, at the middle here, 900. And then at the maximum here, which is 6 inch, so 300 times 6, you can get 1,800. So this is the maximum value, 1,800. Okay, and then for point here at the gear here, so this one is 8 inch. Okay, so previously we have shear force about negative 100. So negative 100 times 8, so it will reduce negative 800. Okay, so 1,800 minus 800, so you will get 1,000 at here. Okay, and then the last one, from 1000 to here. So because this one is 4 inch, 18 minus 8, you get 10. 10 minus 6, you get 4 inch here. So 250 times 4, you get negative 1000. So here is you have already start at 1000. 1000 minus another 1000. So at the end, you will get 0 lah. So let's say if you study at point A. So let's say this one, the thickness is about 1 inch for the gear here, 1 inch. Okay, so what is the moment acting at point A, MA, segment A? So maybe you can assume this gear is symmetry. This one is 0.5 inch. The other one is 0.5 inch. Total will be 1 inch. Point A. So this one is about the distance from Y is point here is about 5.5 inch. So 300 times 5.5. So this is the value of moment A. So you will get around 1650, 1650 Newton meter. Sorry, this one is pound inch. Okay. So let's say you want to study at B. Let's say you assume B will be critical and you want to calculate the bending stress at B. So you need to calculate moment at B. Moment at B. So let's say this one is 6. This one is 0. We have another 0.5 after 6 inch here. We have 0.5. Okay, so 0.5 is around here. Okay, so the area of here is negative 100 times 0.5. Okay, so that's mean you get area is equal to negative 50, negative 50 pound inch. So the total moment at B is the previous moment, which is 1800. This is the previous moment, 1800 minus 50 pound. So then you will get 1750 pound inch. Okay, so this value you're going to put inside the stress equation. Okay. This one, MB. Let's say you want to study or you want to calculate stress at B. So M here you need to change MB. C here you need to calculate. You need to know the diameter at B here. Okay, and then you put inside the formula, you can get stress at B. If you want to get stress at A, so you need to use this value 1650, and then the diameter will be diameter at A here, and the C also will be C at A lah, MC over I, MC over I. Okay, so this is how you want to calculate stress if you have bending load. Bending load. From bending load, you need to draw the shear diagram, and then from the shear diagram, you need to draw the bending moment diagram. Then from this one, you can use inside the equation to calculate the bending. To calculate the normal stress. Okay, still at the bending load. Okay, so some of the point at the bending load, okay, it will produce a maximum shear stress. Okay, so actually if you look at these two graph here, or these two figure here, you can see that if you study at the top plane, you can see the normal stress will become maximum. Okay, you will get maximum at the top. If you study at the neutral axis, neutral axis, the shear stress will become maximum. It depends. So which location that you study. So this one, the location, if you study at the neutral axis, so there is no normal stress. but the shear stress will become maximum. If you study at the outer diameter, you can see here at the top here. So the top will become maximum stress will become the normal stress will become maximum at the top, and the shear stress will become zero at the top. So how we want to calculate your shear stress actually? Shear stress, maximum shear stress at the neutral axis. So it's depend on the geometry of your beam. If your beam is, the geometry will be rectangle, so this is the value that you're going to use, 3v divided by 2a. And if using the circular beam, 4v divided by 3a. If you're using hollow thin wall round beam, 2v divided by a. And for I-beam is v divided by a web. A is actually the area, area of the cross-section area lah. And what is V value? V actually the shear load, not Poisson ratios. V is shear load. Okay, so how you want to get this V value is depend also on the location of your study. Okay, so let's say if you study, you study at this point, okay, so the shear load will be at this point, shear load will be at here, so the value will be 300. Okay, if you study at this one, at the middle here, the shear load will be here, negative 100. This is the shear load. If you study at point A here, so the shear load will be at point A, this one is point A, 300 also. If you study at the middle of the gear here, okay, the middle here, the shear load will be 300 plus 100, total is 400. So that is the value of V. You need to check where is the location. If you assume this one will be critical, then you need to use 300 lah for your V. And for your bending, you need to use MA here, 1650. Okay, and then for the torsion, where is the load is T, okay, top. Okay, so you can calculate the shear stress is, the formula will be TR over J, where T is the top, R is the radius, J is the polar second moment of area. The same figure you need to check for the J value, which is figure appendix A18. A18. Appendix A18. Oh yes, this one. A18. Okay, so if using non-circular cross-section, if you're using maybe rectangle, so for the rectangle, you have a shape of B times C. And then if you want to calculate the top for the rectangle shape, so you're using this kind of formula, which is T over BC square times in bracket 3 plus 1.8 divided by B over C, where B is the longer side and C is the shorter side. Okay, let's see. So we have this one. We have a top for the rectangle. So B is the longer side. So this is your B, this is your C. Okay, so just use this value inside this equation to get the value of T max or tau max here. Okay, so for torsion, mostly it's not going to give you directly. The top value is not going to give you by directly. you need to calculate the value of T or torque. So how you want to calculate the torque? So mostly the torques come from the power, from the power. And there is the relation power is equal to torque times the speed, torque times the speed. And if you are using the imperial unit, so the top one is imperial unit, and the bottom one here is using the SI unit. So this is H is equal to power. Power is equal in horsepower. This one is imperial unit. Power in horsepower. And from here you can calculate your torque here by if the power is given and the speed is given. So your torque will be power times this one, this value 63,025 divided by the speed here. N is shaft speed in RPM, revolution per minute in RPM. Okay, you can use you can choose lah whether you want to use this first equation, second equation, third equation, or fourth equation. Okay, so all of this will have the same value lah. It depends whether when you want to calculate the force or whether you want to calculate the value of torque. And then for the SI unit, so SI unit, the equation is power is equal to tau omega, where omega is the angular velocity, radian per second. Okay, so if you has speed in RPM and in RPM, rotation per minute, you need to calculate the omega from this RPM first before you can use this equation, where omega is in mechanic of machine. If you check again in mechanic of machine, the equation will be 2 pi n over 60. Okay, omega is 2 pi n over 60. Okay, n is your RPM lah, speed in RPM. Okay, and then you can calculate, you can get your torque here. Okay, maybe this one is simplified. They have already simplified for you. Torque is equal to 9.55 times H divided by N. H is power in kilowatt, in watt. N is the speed, is speed in RPM. Okay. Okay, and then this stress concentration. So actually, for next chapter, which is chapter number 3, so this one will not going to affect much. Okay, so I think this one you can ignore it first, because this one we will discuss more detail in chapter number 4. Okay, so you can ignore this one. We'll discuss detail in chapter 4. Because for static theory, it's not going to affect much. So only for fatigue. Fatigue will, if there is a hole or there is a discontinuity object inside the beam or something like that, so the stress will increase. The increase stress, because there is stress concentration happen here. So this one I will discuss detail in chapter 4. So this the same thing here. So this one is stress concentration factor in chapter 4. Okay, we look why parts fail. So actually parts fail when we have the stress acting. Stress acting is higher than the strength of the object. Okay, so the part will start to crack. Actually, is happen at the surface, at the space. So the crack will start at the surface, and then it will propagate inside the material, and then the part suddenly will become broken. It will become break. Okay, so this start with small crack at the surface. So in order to make sure your part is safe, so you will calculate the safety factor. So this is the general formula to calculate safety factor, where we want to compare strength, strength divided by stress. Okay, stress, you need to use your maximum stress, and strength, you need to use your yield strength. And because after the yield, okay, you can see that there will be a permanent deformation. So we don't want that deformation happen to your parts. Okay, when the deformation happen, your parts you already fail already. You need to replace the parts. Okay, so that's why the safety factor, N is the safety factor, is strength, yield strength divided by the stress. Stress here is your maximum stress. Maximum stress. Okay, so make sure to make sure this strength is bigger than stress, so N is must be bigger than 1. So when N is bigger than 1, so your part will become safe. When N is less than 1, then your part will become fail. Okay, so what's about if N is equal to 1? Is it safe or fail? Anyone? Is it safe or fail? What do you think? Safe. Yes, it's still safe, but this one actually we call it as critical. Okay, it's going to be fail if you put just a little bit force. Okay, so this one we call it as critical. Okay, so N is equal to 1, safe. N is less than 1, fail. N is equal to 1, we call it as critical. So in design, in order to make sure your parts is always safe, so we want to calculate the maximum stress allowable. This one is, we call it allowable stress, and this is the maximum stress that you allow to make sure that your part is still safe. So allowable stress is equal to failure strength divided by design factor. So what is failure strength? Failure strength is same here. Your SY value, SY value. Design factor, maybe you can put N that you want to put here must be bigger than 1 lah. Must be bigger than 1. If you put less than 1, actually that one is not allowable stress. Okay, so this is some reference for you if you want to put, you want to know what is the suitable, what is the suitable value for safety factor lah. So we have brittle and ductile. Maybe you can look the next slide here. Okay, so you can put safety factor 1.25 up to 1.5 is if the material properties known in detail, operating condition known in detail, load and resultant stresses and strain known with high degree of certainty, material test certificate, proof loading, regular inspection and maintenance, low weight is important to consideration. That means you can put the lower safety factor if you know everything lah. You make sure that everything is correct. And if you most of the thing is unknown, you need to put the bigger safety factor, 3 to 4. 3 to 4 should also be used with better non-material that are to be used in uncertain environment or subject to uncertain stresses. Okay, so in between here, between minimum and maximum, you can read here. Maybe for your project, maybe you can use between 2 to 2.5 safety factor lah. Okay, so this is some guideline for you to check what is the suitable safety factor that you can use. Okay, I think this one just some explanation how the factor affect the safety design factor, the safety factor lah, or design factor. So this is you need to consider application of the load, environment. You want to put where is your, you want to put that thing, the load, type of stresses and material, and also confidence level. So all these things will affect your design factor. Okay, so I think this one you can read by your own. Okay, because I want to proceed with some example here. Another about 1 hour. Okay, so let's do the exercise. Example 1 here. Okay, so from here, so you can see from first here we need to calculate what is the maximum, maximum normal and maximum shear stress at point A. So you need uh, to draw the free body diagram. Starting with draw the free body diagram, and then from the free body diagram, you need to calculate all the load at the free body diagram. And then from the load at the body diagram, you need to change or to calculate the stress. And then from the stress, you need to calculate the maximum stress. And then from that, you want to compare with the strength, whether the part is safe or not. Okay, so we have a crank here loaded by a force of 300 pound. So this is, we have 300 pound here that will cause twisting and bending to a 3/4 inch diameter. So this is the rod, have 3/4 diameter. Okay, fixed to a support at the origin of the reference system. Okay, at the end here, we going to assume this one will be fixed. So in actuality, the support may be an inertia that we wish to rotate. But for the purpose of a stress analysis, we can consider this is a static problem. Okay, maybe this one will going to rotate some device or some machine, machine. So we want to check whether the part is safe or not. So we need to fix this one in order to check what is the maximum stress acting at the point A here. Okay, so why point A? Because you will get the maximum stress at point A. Okay, so draw the free body diagram of the shaft AB and the arm BC. They ask you to draw a free diagram AB, BC, and compute the value of all forces, moment, and torque that act. Label the direction of the coordinate axis on this diagram. Okay, so which one you want to calculate first? Whether you want to calculate at the rod or whether you want to calculate at the arm? Which one? Any suggestion? From point A. Yeah, because we want to calculate at point A. But if you, in this question, they ask you to calculate both, at the rod and also at the arm here. So it's much easier if you calculate at the arm, because the arm, the location is near to the force given. Okay, so you need to calculate at this arm BC first, and then after that you want to transfer all the forces acting at the arm BC to rod. If they ask you to calculate at A here, okay, then you need to transfer this force at the end of B. No need to calculate this C. But in this case, they ask you to calculate both component, BC and AB. So you calculate at BC first. Okay, so we draw the free body diagram. Just draw a straight line. Okay, so this is arm BC. Okay, so you need to transfer the force, F here, at the end of C. Okay, so the force is acting the same direction, which is downward. we have F. So before that, maybe I can put the axis. So we have Y direction at the top here. We have Y direction. And here we have Z direction. And here we have X direction. Okay. So because there is a distance between C to the force here. Okay, so there is a distance when you transfer F here. So you need to put also the torsion, because this force when acting at the small arm here is tend to twist, or to rotate this arm BC. So there is a force, torsion force, okay, in this direction. Top. Okay, maybe I put top C, top at C. Okay, so this is the acting load. This is the acting load, F and TC. The reaction load will be acting at the end of B here. So for the reaction load, you need to put the same force but in opposite direction. So we have force acting downward here. For the reaction force here, you need to put force acting upward. Okay, and then this one, torque acting clockwise. And for here, you need to put torque acting counterclockwise. TB. I just put TC2 lah, TC number 2. Because when we study at AB, we have B also, right? That's why I just put TC number 2. Okay, so is it the force is already in equilibrium? Or you need to put another force? Macam mana? It's already in equilibrium or you need to put another force? So if I draw, maybe in two plane, let's say I draw in Y and Z direction. And this one YZ, YZ, okay. If I draw in YZ direction, this one is Y, this one is Z direction. Okay, so you can see this is your arm. Okay, so you have force here. You have another force here. And for the torque, you cannot see the value of torque because it's normal to the plate. Okay, but if you want to put the torque, you need to use the right hand rules. Okay, so if you use the right hand rules, so this is the rotation. Okay, so you need to put your finger at this rotation, your forefinger, and then your thumb will be the direction of torque. Okay, let's say if you put the other forefinger is in this direction, your thumb will be at this direction. Okay, so you can put the torque here. The direction of torque is here. If you're using the right hand rule. And then in this case, okay, so this is the direction for the forefinger as beside the thumb, and the thumb will be put this direction. Okay, so this is the top, top C, and the top C1. So is it already in equilibrium? Torque, and we have torque here, we have torque here. Okay, it's already we already equilibrium for the torque. We have force here is already in equilibrium. The value is same, but because this force is acting at the certain distance here, okay. So the force is tend to make this road, this, what we call this one is the arm, the arm to rotate in this direction. Okay, to rotate, the force is these two force tend to make this arm rotate in this direction. So in order to balance it, you need to put the moment at here. You put moment at here, to cancel this kind of uh, rotation. So moment. So that's mean you need to put moment on x-axis here. Moment at B. Okay, and just put moment at B. Okay, so this is already in equilibrium lah. So after that, you can calculate the value. So F is equal to, it's already given 300 pound. Okay, and then TC is F times the distance here, 1.5, which is 300 times 1.5. So you will get 450 pounds inch. Okay, and then the moment here, the moment at B is equal to the force times the distance from here, which is 4 inch. 4 inch. So F 300 times 4, which is 1200, 1200 pounds inch. Okay, so that's all the forces acting at the arm BC. Arm BC. This one is B. This one is C. Okay, and so we already calculate lah all the force F, TC. TC1 is actually same. TC1 and TC is actually the same value. Okay, and then after that, you can transfer all the forces acting at point B here at the arm BC to the road AB. Okay, so we need to draw. Okay, so when you transfer all the forces from here to here, so let's start with F here. F, okay, is upward, and then when you transfer to road AB, we're going to be downward lah. Okay, this one is A, this one is B. Okay, and then I put the axis. This one is Y axis, this one is Z axis, and this one is X axis. Okay, so F here will become action force for road AB lah, and then MB here, this one will rotate counterclockwise. When we transfer here, it will rotate clockwise. Okay, so, but you cannot put the name moment anymore because moment actually it will make the this road will become bend, but this one it will rotate the road at the axis. So this one you cannot call it as a moment anymore, so you need to change the name into torsion. Okay, torsion, because it will rotate the road, not bending the road. Okay, so MB here, when you transfer here, it will become torsion. So I think I need to put the name, the new name will be TB. Okay, so MB is equal, sorry, TB is equal to MB. Okay, so the value will be the same. And TC here is rotate at counterclockwise on Z direction. When I transfer here, it will rotate on clockwise on Z direction. Okay, this means we rotate about here. Okay, so this one will become bending. Because it will bend the road of AB. So from torsion, I need to rename it as bending. So this one maybe I just put MB. We have already MB here. Maybe just put MRB lah for MAB. Okay, MAB. So the MAB is actually the value of TC1 here. TC1 or maybe TC. Okay, the same value for TC. Okay, so we have already transferred all the forces acting at B from AB, arm AB to road AB. Okay, so and then this is the action force, and then you need to put the reaction force at the end of A here. Okay, so the direction will be opposite direction for this one. Okay, so we have F here, and then this one MAB. So we have here. Okay, and then we have torsion here. This one is clockwise direction. If you look at x-axis, this one will be counterclockwise direction. Okay, top A lah. Okay, top A. So again, I want to ask you, is it this free body diagram is already in equilibrium?
Yes.
Yes. Okay, so let's check at the by using the plane. So if you want to look at the plane here, we look at the y-x axis because one the road is on x-axis. Okay, and most of the load will be at f-axis. So you need to look at the y-x axis. Y is at the top, x is at your right. Okay, and then we transfer all the force. So we have F here, and we have another force here. Okay, for the torque here, so the direction, if you look your right hand, the direction will be inside. Okay, the torque. From here, the direction will be also inside. And then for MAB, so we have MAB here. and we have another MAB here. Okay, so you can see torque and torques is already same value, direction is already same, so they will cancel each other. And MAB also same value. Okay, F and F is also same value, but F and wait, this F, you can see they are not acting at one straight line. They're acting at some distance here. Okay, so that means there is another movement. It's tend to rotate. It tend to rotate at this direction. Okay, so to cancel this movement, you need to put another bending, bending load over here. So which is MAB2. Okay, where MAB2 is equal to F times the length of the road here lah. Okay, F times the length of the road. Okay, so the total force is F is the same value, 300 pound. Okay, and the torque here, which is torque is equal to moment B. Moment B is 1,200 on inch. Okay, and then MAB is equal to TC. TC is 440. Okay, and at the left side here, we have F, the same value, torque, the same value, 1,200. MAB is the same value, MAB2. F times L, F is actually 300. And the length of this road is 5 inch, 5 inch. Which is, you will get 1,500 pound inch. So actually, you can combine both of this moment. And you can combine both of these by using one moment here. Okay, so where I want to put here, maybe I just put somewhere around here. Okay, so this is MA total. Okay, if you put MA total, you can erase this one, you can ignore this one. So MA total actually is equal to 450 plus 1,500. Then you get 1950 pounds inch. Okay, so we have already calculated all the forces. Do you have any question you want to ask? Ada yang angkat tangan ya?
Yes, Doctor.
Yes, yes, Daniel.
Why do you put moment at road BC tadi?
Road BC. This one.
Yeah. Yes.
Okay, road BC. So if you look here again, the road, this one is arm BC. So we have F here, we have torsion here, and then to calculate or you want to draw the free body diagram in equilibrium, you want to make sure you need to put the opposite direction of F here, torque here. Okay, and then if you look properly, F, TC, and TC here is in straight line, you will cancel each other. But F here, you can see is not in straight line. As the second force is acting at the end, another force is acting at the end. So you will tend to rotate at the clockwise direction for this arm. So in order to make sure there is no this one is not able to rotate, you need to put the bending load here at the fixed location. Jadi at the fixed location, you need to put the bending load. Okay, so that's why M here is actually F times the distance and the length of this arm. F times 4, you get 1,200. Okay, so that's why you have to put this F. If you look in appendix, so there are some guideline for you, which is shear moment and deflection of beam in table A9 in table A9. Okay, so if you have this kind of situation, you have force here, you have force here. Okay, you need to put the bending moment at the fixed location in order to make sure this one is in equilibrium. The same thing lah. You have here, you need to put the bending moment at the fixed location to make sure this one will be in equilibrium. If not, then the one will be attempt to rotate. Okay, you can see some other example. Okay, in our case, so let's say we have it's similar like this. Look, this kind of situation. We have force here, reaction force, and then in order to make sure this one in equilibrium, you need to put the moment. The same thing lah. In our case study here. Okay, and we have force here, In order to make sure in equilibrium, you need to put the bending load at the end of here. Okay, the same thing here. Ini this one you can see we have MAB, but the value is same. If the value is same, it will cancel each other. So we have F and F here. So this one there is no moment that going to tackle the this rod able to rotate. So that's why we need to put another bending load, which is F times L. And then the total bending load, you need to sum of both these two. Boleh?
Boleh. Thank you, sir.
Okay. Okay, so we just check the answer. Okay, so at C here we have 300. Okay, negative 300, which means downward. We have torsion 450. Okay, I think the same value. At here we have 300. Positive, that means upward. And we have a bending load of 1,200. Okay, this one the bending load. The same action. If you want to put in 3D, you can put this one. The direction is here. If you want to put using this kind of technique, you need to use your right hand rule, right hand, and then this is this is your rotation of your finger, the forefinger, and this one is the direction of your thumb. Your thumb is direction here. That means you put your M here lah. Okay, I think that this one is the same. Okay, and then for rod AB, so we have acting force 300. Okay, and then we have bending load 1,000. Torsion is 1,200 and bending load 450. And then at the end here we have 300. The torsion is 1,200 and the total. This one is the total bending 1950. Total bending 1950. So we get the same answer lah. Okay, and then for the second one, for the B, compute the maximum of the torsional stress and the bending stress in the arm BC. This one is the arm BC. Okay, so you need to look at this free body diagram, arm BC. Okay, compute the maximum and torsional stress. Maximum stress and the torsional stress, which is the shear stress lah. bending stress is MBC. So first thing you need to find where is the maximum or the critical location. You want to calculate this one and shear. So where is the critical location? You know that the bending is the formula is MC over I. Your shear will be TR over J. Okay. So if you look at this is the free body diagram. You cannot find where is the maximum moment unless you draw the shear diagram, shear and bending moment diagram. Okay, so you need to draw the shear bending moment diagram. So let's say this is your F 300. This is your another F 300. For the top, maybe you can ignore. And we have a bending here, which is 1,200. Okay, and then for shear diagram, this is your V. Okay, so you have force acting upward, which is 300, and then the force will become constant. This one is your zero value. This one is 300. Okay, and then you're going to down back again, become zero again. So this is your V diagram. Then for the bending moment diagram, okay, so we have a bending load which is 1,200. That means we're starting with 1,200. Okay, and then the length of this one is 4 inch. Okay, you can calculate 300 times 4, you get the area of it is 1,200 lah. And then actually your bending load will be decrease and then will become zero at the end of it. This one. So from here you can see that the maximum bending load will acting at B here. This one will be critical location lah, because we have a bigger moment load at here. And for torsion, actually the torsion is same. Let's say this is your arm. The torsion value is 450. So it will be the same or maintain all over the arm, 400. Okay, this is the top. Okay, so if you combine of both moment and torque, so you will get the critical will be acting at the end of B here, at the end of the B. So after that, if you look at here, at B here, so okay, so at B we have some. We have another location, another possible location. So where it will become fail, whether at the top or at the neutral axis, at the bottom, something like that lah. Okay, but mostly this one if you have two kind of stress, okay, which is bending stress, and this one is we have bending, and because this one when you put over here will become bend and become bend here. Okay, so at the top we have the normal stress. We have the normal stress at the top. If I put in this direction, when you try to push this arm, so you will have a force or stress in this direction, because it will become a tension at the top. At the bottom will become compressed. It will become compressed. At the middle or at the neutral axis, what happened? the normal stress will become 0, but the shear stress will become maximum. I've already discussed previously. So at the neutral axis, the shear stress will become maximum, but the normal stress will become 0. So actually the critical is mostly happen at the top, because if there is bending load, so bending load will produce two kind of stress, maximum and also shear. So if you compare these two, mostly the maximum stress is always bigger than the shear. So that's why I proceed with the at the top. No need to study at the neutral axis. Okay. So we have stress in this direction, which is on this one is on z axis, sigma z. Okay, and then we have a torsion. We have a torsion in this direction. Okay, when we have torsion in this direction, that means we have a torsion also in this direction. Okay, so this one is tau. This one is z. This one is y. Zx. Sorry. So this one is z. This one is x. So tau zx. Okay. So we have this kind of stress. I think at B, at point B here, sigma z on this direction, and tau zx and at this direction. Okay, because the torsion is here and here. Okay, so if you transfer the top, if the torsion is here, then here the direction will be here, here, and because this one is near to here, and then the direction of top will be here, tau zx. Okay, and then you need to calculate this stress and this shear stress. Okay, so this shear stress is because of this bending load M here, which is the M is 1,200 here, 1,200. So you can calculate sigma z. The formula is MC over I. M is actually, you need to use M at B here, MB. C over I. MB is 1,200, already calculate here, 1,200. And C is the neutral axis. This one is 1 over 4. Okay, so C is half of these two, and 1 over 4. This means 1.25 over 2. And I, because this one is rectangular. Okay, this one is rectangular. You can see that the cross-section area will be like this. The cross-section area is rectangle. Okay, and the neutral axis will be like this. Okay, so if you look at the formula, chapter appendix table A18 here. Okay, so this is your B, this is your H. Okay, then your I will be, I will be, which one I want to use, IX or IY? Okay, this is your neutral axis, and let's say that we discussed before. Okay, so the neutral axis will be at here. Okay, that's mean if you bend this one, I need to use this kind of equation because the neutral axis is intersection with this line H at H, not at B, not at B. So this one will be H power of 3 divided by 12, BH power of 3 divided by 12. B is what? B is 1 over 4, 0.25. H is 1.25, H 1.25, B is 0.25. E, H power of 3, H power of 3, 1.25 of 3 divided by 12. Okay, I need someone to help me to calculate this one and just give me the answer. So anyone can give me the answer? 23,040. Okay, thank you. 23,040 psi. Or you can put 23,000.04 kpsi, kilopound per square inch. So this is the value or stress if you want to calculate in imperial unit. Then for the torsion x, sec x. Okay, because this one is not in circular cross section, so this one is rectangle. So you need to use the previous equation to calculate torsion, which is which slide? Okay, this one. Okay, so T is 400. Sorry, where is T? TC is 450. Actually 450. I'm doing some mistake here. Okay, so T is 450 divided by B. B is the longer side, C is the shorter side. So B will be 1.25, C will be 0.25 lah. Then times 3 plus 1.8 divided by longer side is 1.25 divided by 0.25. Okay. Please calculate and give me the answer. $4,838. 4,838.4. Okay, PSI. Okay, is it correct? Let's compare the answer. Okay, so for B, we get 18.4. Why we get different value?
Doktor, sir.
Yes. Apa silap?
Calculation, saya dapat 18,432 for the stress and
The stress, this one, or not 23,000.
yeah, and for the next one is
The-
19.
All the value is here correct.
Yeah.
Oh, cuma dia final answer je lah. Okay.
Yes.
Berapa tadi? 18,000
18,432.
for
32.
3 Okay, 18.4. KPSI. Okay, and then for shear,
Shear 19,353.6.
19
353.6.
53.6. Okay, so about 19.4 KPSI. Yeah, 19.4 KPSI. Okay, betul. Okay, next. So because they don't ask you to calculate maximum shear stress, they just maximum the torsional stress and bending stress in arm BC, maximum of the torsional stress and bending stress. Okay, they just you to calculate the maximum bending stress and shear stress. Okay, they don't ask you to calculate the maximum or the principal stress. If you ask you to calculate the principal stress, so you need to calculate sigma 1, sigma 2, and sigma 3 at this location. But in this question, they don't ask you to calculate this one yet. They just ask you to calculate the normal stress and the normal stress and the shear stress that is maximum. Okay, and then number C. Okay, any question? If you have any question, just ask. Okay, if you don't have any question, I will continue. We have another about 25 minutes, 20 minutes, something like that. So C, locate a stress element on the top surface of the shaft A. So let's say we want to, this is shaft A. So we want to study at the top here, draw some element and calculate all the stresses or the stress component that act on this element. So because we have three load at B here, so you can see that this one at B, we have force acting downward. We have this one, this one is what? Bending load. Okay, and then we have a torsion load. Eh? So all these forces will make a stress at point A here, at the top of point A here. Okay, so you need to calculate all the stresses because of this force. Okay, so first we look at, maybe I just erase this one first. So at B here, okay, we have a torsion. And then we have a downward force F here. Okay, and then we have a bending. Okay, so what happened if I put a F here? Okay, I just press a downward force at B here. What's happened to this element? So as you can see, at A here, okay, when I press this one downward, there will be a tension at this side. Okay, it will produce stress on this side, which is sigma on x, sigma x. Okay, and then what happen if I have a torsion load that rotate clockwise direction for x here? So you will have shear, you have shear stress at here. This one is tau xz, tau xz. Sorry, xz. Okay, and then what happen if I have a bending load, a bending moment here? Moment here will make another kind of stress at this direction. Okay, so if you look, if I try to draw this element outside from here, maybe here. So this one is x axis. This one is z axis. Okay, so you have a force or stress in this direction, which is sigma x. And sigma x is combination of F and also bending load. I just put one. Okay, and then this one also sigma x. And I have another shear in this direction. Okay, which is tau xz. Okay, so because the bending load here, I will going to use the total, which is M is equal to 1950 total bending load. So that's mean no need lah, no need to calculate F and M anymore. You just use the total, the total bending load. Sigma here, use the total. So M total times C plus I. If you want to get the bending stress. This one, T, what is this one? T, ni tadi, TAB TB or TA, TA. Okay, TA time radius divided by J. If you want to get the tau exact and sigma x at this site, which is at point A. Okay, so let's calculate. Okay, so we calculate sigma x first. Sigma x is equal to M total, which is 1950. C 3/4 inch. 3/4 inch. Maybe I can try to simplify this equation first. So let's say the equation is MC. C is D over 2. I is pi D power 4 divided by 64. This one, D and D can cancel each other. So you can have D power 3. 2 and 64, we have 32. And 32 you bring at the top. So the final equation will be 32M divided by pi D cube. Okay, and then we change the value. M is 1950. D is 3 over 4, which is 0.75 inch out of 3. Okay, and much easier lah if you cancel the parameter. Okay, fine. Someone calculate and give me the answer.
Uh, 470 at 1.56.
47081.5.
0.5.
The unit will be in PSI. So let's simplify it. This one will be 47.1 kpsi. Okay, so and then for the torsion, the formula will be T R over J. R is D over 2. J is pi D power 4 divided by 32. Then this one 3, this one is 16. This one is, okay, cancel each other. Then you will get 16T divided by pi D cube. Okay, and then we just put the value 16 T TAB TAB T is 1200 1200. D is 0.75. Okay, so give me the answer. 14,486. Lukman, betul This one for this equation, saya baru tengok.
Yes, torsion.
14.486. 14. Okay, sorry. 14,486.6 psi. Okay, so around 14.5 psi. Okay, so this will answer for the question C. So this is the stress that acting on the plane. Acting on the plane. Sigma, and we call it as plane stress. Okay, plane stress. Sigma x because we have on x axis, and then we have tau xz because we have shear stress on x and z axis. So we call this a plane stress. Okay, so let's compare the answer. Okay, so we get 47.1 and 14.5, almost the same lah. The same, we get the same answer. Okay, good. So the next one, for D, determine the maximum normal and shear stresses at A. The maximum normal and shear stress. They ask you to calculate the principal stress actually. The principal stress, which is sigma 1 and sigma, principal stress, which is sigma 1, sigma 2, sigma 3. And this one for normal stress, maximum normal. And then maximum shear. Maximum shear, you need to calculate tau 1, tau 2, and tau 3. Then from this tau, which one will be the maximum? Okay, so this is the principal stress and principal shear stress. Okay, so how you want to calculate? You just use the formula. No need to draw the more circle. Just look back at the formula. Okay, so this is the formula. Okay, so because we want to calculate at point A, so that's mean you need to use sigma x, sigma y, sigma z at point A. So because if you look at point A here, we have only sigma x and z because point A is located at the top plane. So we have axis x, we have axis z. That means we don't have axis on y direction, only x and z direction. So that means you need to change a little bit from the here. So for sigma z, you need to change, for y, you need to change z direction. So 1 tau x z. Okay. So sigma 1 is equal to sigma x. Sigma x is is it 47.1? Sigma Z is we don't have we don't have anything on Z direction here. I don't have any stress on Z direction. This means sigma Z will be 0 divided by 2 plus plus sigma X 47.1. What is this thing? Minus 0 divided by 2. Then this one is square. Then plus tau xz. Tau xz is 14.5 square. And then the rest is square root. So can you calculate this one first? 47.1 divided by 2. So give me the answer of this. 47.1 divided by 2, you get 23.65. 65
23.55.
Oh, sorry, 23.55. Okay. Then give me the answer in this one. Square root.
Uh, 27.66.
27.66. Okay. And then just plus these two, you get about 51 point. Apa tu? 11. 21 51.21. Tu Is it correct? I think it's correct. Good. 51.21. KPSI.
Betul.
Okay, and then sigma 2, just minus these two things, 23.55 minus 27.66. Okay, so give me the answer. Negative 4.11
Yes, negative 4.11.
KPSI. And sigma 3, because sigma 3 is acting normal, normal here. So there is no force at the top here. So sigma 3 is assumed 0. Okay, so this is all the principal stress that you already calculate. Sigma 1, 51.21. Sigma 2, negative 4.11. Sigma 3 is equal to 0. Okay, and then tau, the simple shear stress, simple shear stress, tau 1, 2. Tau 1, 2, how you want to calculate tau 1, 2, just use these two value lah. Okay, tau 1, 2 is 51.21. Because if you look properly at the Mohr circle, so this, let's say this is the Mohr circle. This is the straight line at the center of the circle. Okay, so we have sigma 1 here, which is 51.21. Sigma 2 we have 0. Okay, that's mean okay, so that's mean this one is 4.1, negative 4.11. Okay, this 51.21, 4.11, and another stress is 0 here. Sigma 3 is 0, which is here. So if you draw a Mohr circle, we can get there is 3 Mohr circle. Okay, the first one is here. Second one is here. The third one is the biggest one. Okay, if you can see here, the maximum, the tau max, will be acting at the bigger circle, at the bigger circle. So which is tau 12 lah, which is what tau 12, not at the tau 13 or not at the tau 31 or this one 2, sorry, 23, 23 is small. 12 is, sorry, 13 is also small. This is 1, this is number 2, this is number 3. Okay, so the biggest shear stress will be acting at the tau 12. So you just need to find tau 12, which is, if you can see, tau 1 minus tau 2, sigma 1, and this one is sigma 1 value minus sigma 2 value. Actually, you get the diameter, the diameter of the circle. And if you divide this diameter into half, you get the radius. And you get the radius. This is the radius of the bigger diameter. Actually, this radius and this one actually the same radius. This one radius and this radius is the same one. That's why tau 12, you can simplify the equation to sigma 1 minus sigma 2 divided by 2. Sigma 1 minus sigma 2 is the diameter. Divide by 2, you get the radius, and then you will get this one. So tau 12. Okay, just use a simple like this lah. Okay, no need to use the equation. Actually, if you use the equation, you get the same value, which is 27.66. This one minus this one, you get 55 something. 55 divide by 2, you get 27 again. 27.66. Okay, so that's the answer for the principal stress at the location A, at here. And after this, we are going to use this value into the theory of safety factor. Okay, if they ask you to use sigma 1, sigma 2, sigma 3, then use this one inside the equation. If they ask you to use tau max, just use this value inside the equation to calculate the safety factor for next week. Okay, next week we try to calculate safety factor, and we want to check whether n is bigger than 1, n is less than 1, or n is equal to than 1. If bigger than 1, it will safe, and less than 1, it will fail, and is equal to 1, it will become critical. Okay, for this chapter 2, it just proceed up to the principal stress and principal shear stress, or tau max. Okay, so any question?
For not
No,
today.
doctor.
No, okay. So you just check the answer. For D, yes, 27.7. Maximum shear stress is 51.2. Sigma 2 they not calculate. Sigma 3 also not calculate. Actually, sigma 3 is study 0, is 0. And then the maximum shear stress will be at tau 12. Okay, so I think it's already 11 o'clock. So that's all for today. And example 2, please study by your own, because this one actually you have already done. So next week I'm going to start with chapter 3. So that's all. Thank you very much, and see you on next week.
Thank you, Doktor. Boleh nak minta attendance tak?
Attendance.
Tadi dapat nak scan.
Also me, Doctor.
Thank you, sir.
Okay, sama.
Thank you, sir.
Okay.
Thank you, doctor.
All right.
Thank you, Doctor.
Terima kasih, doktor.
Okay, sama.
Terima kasih doktor.
Okay, sama.
Terima kasih doktor.
Okay.